In the previous session I said I would introduce to you a relationship between the size of a quotient group and the size of its group, G, and the size of its subgroup, H, the normal subgroup. Well, to derive it, so let's let H be just a normal subgroup of G, okay? We don't know how many cosets it will have, but whatever it is, it'll be some integer, so let this group have p cosets, formed from your subgroup H, your normal subgroup H. Okay, so you'll have p of these cosets. Now, cosets, they're all of the same size, because what is a coset? It's just any element G, little g, from your group, and you multiply, if it's a left coset, so you multiply all the elements of your subgroup on the left by little g. Okay, so that'll give you it'll rearrange the order of the elements in H, but it won't change the number of elements in H. So the size, number of elements in the set GH is just the same as in H. Okay, so that's true. So for all cosets of your H, they'll all be the same size. They'll all have the same number of elements. Right? So you've got this. So all cosets have the same size. Now this was a critical factor in the proof of Lagrange's theorem, if you remember. Okay, so all cosets have the same size. Now your in the context of quotient groups, your G is a union of disjoint cosets. And I haven't drawn out the whole table, but here's a table for D4, right? The symmetry operations of a square, D4. Okay. Now, so here's your subgroup H here. So it consists just of two elements, E and A squared. Now it's D4, right? So it has generators A and B. And then you arrange your row here in cosets, right? So H, this would be AH, this would be BH here, and this is BAH, and similarly this way, right? Now, all these elements here, so you've got 4 times 2, so you've got 4 cosets, right? 1, 2, 3, 4 cosets. And each of them are of size 2, so that, it's not surprising. Cosets are all the same size, right? But all these elements together, that's G, right? Because G is a union of disjoint cosets. Okay, then you can have the size of these cosets is now all these cosets have the same size as each other. So what's the size of H? That'll just be mod H. That's the size of H. And now if you have P of these cosets, the number of elements total in your group, this, will be P times the size of your coset, right? Because you've got P cosets, and that's the size, or the number of elements in a coset. So you've got this relationship, right? The size of your group is just the number of cosets times the size of a coset, right? Because G is a union of disjoint, all different cosets. Okay. But this quotient group that we're forming, these cosets are the elements of the quotient group. Right. So what's the size? The order. What's the size of your quotient group? Well, it'll be the number of cosets, right? In this case, 4. We've got 4 cosets, so our table will be 4 by 4, so 16. So the size or the order of your quotient group, that's this, right? Its order will be equal to the number of cosets. Okay, follow that? Which is P. But what is P? Well, P is G, mod G divided by mod H. So P is, all right? Now, since that's P, and from here P is G, mod G divided by mod H, okay? So therefore this which equals P equals that. So here you've got this very simple relationship between the size of your quotient group, and it's just the size of your group divided by the size of your subgroup. Right? It's pretty simple. So if you want to find the size of this, you just look at the size of your group, divide it by the size of your subgroup. And that's it. Really easy. Now, perhaps, now I can rewrite this. I can take this H over this side, like this. So I get the size of the group is the size of the quotient group, or factor group, times the size of the subset. Now, if you look on it in this form, you can probably see why this group is called a quotient group. It's the result of a division. Okay? But if you look at it in this form, and the two are utterly equivalent, if you look at it in this form, this group here is a factor of this one. Okay? So you could sort of say this is a factor group, and here it's a quotient group. So that's why the two are used virtually interchangeably. Sometimes I'll talk about the quotient group, other times the factor group. I think factor group slips off the tongue more easily, but anyway, it doesn't matter. The two are synonymous and both used frequently. All right. Okay, so we know how to find the size now of a factor group. Very easy, just divide the size of the group by the size of the subgroup, the normal subgroup. Important. Okay, let's do an example now. Let's actually find the quotient group. Given your original group G, big G. In this case, it's D6. So it's a dihedral group, 6 sides, equilateral hexagon. So 6-sided figure of equal lengths, 6 equal lengths. So this symmetry group, this group is the group of the symmetry operations of a regular hexagon, okay, D6. And you're given a subgroup, here it is, it's E, the unit, and A cubed. And you're asked to show that this subgroup here is normal, right? And then you also asked, now if it is normal, then you can create a quotient group. You just divide D6 by H, right? Here's your quotient group. And that that can be done if H is normal. Right? So our first step is to show that H actually is normal. And then you will get this quotient group, and you're asked, what is it isomorphic to? Right? Like this resulting group that you get by division. Now it's a matter of speaking, right? Strictly speaking, this group is just a group of cosets. Okay. So the group that results, what is it isomorphic to? Like what is this group in effect? This quotient group. What is it? All right. So our first step is to prove that it's that H is normal. And remember from the previous session, to prove that H is normal, you do not have to prove equality here. I mean, if you had equality here, strictly speaking, that's the definition of H being normal. But from theorem, what was it? 59? Is that correct? Hold on. What number? Yeah. From theorem 59, if you have this, if that's true, then this is actually equal to that. So let's just use this one. Okay, so we have to show for H, which is here. So this subgroup. Now, it is a subgroup, E and A cubed. That's a subgroup. It's a group in its own right. And these are elements of D6. D6 will have, well, Dn in general has 2n elements. So D6 will have 2 times 6, so D6 has 12 elements, and these are 2 of them. Alright? So we have to show for each member of H, the subgroup, which is, well, only 2 of them, is E and A cubed. So we have to show for all members of your group, big G, for any member, this is true for all little g, any member of your group, you have to show that this, for each member of your subgroup, that it belongs to the subgroup, in a sense closed. The result of this belongs to this set, right? Now a bit of revision about dihedral groups. Now it's D6, and it's a dihedral group, so it will have 2 generators, A and B as usual, and A to the n, where n is the number of sides of equal length, and A to the n is E. For this case, n is 6. Okay, so A to the 6th is E. Right? These are the relations of a dihedral group. Right? So A to the 6th is E, B squared's always E. B is just one of the flip operations in dihedral groups. And ABA is B. Now you've seen this quite a few times now. So they're the relations in the presentation of this group, right? The description of this group. Right? Right, so H contains just 2 elements, E and A cubed. So let's do it for E. Let's put an E in here and see if this result here, for whatever element we choose, see if it belongs to H, this set, or subgroup actually, that consists of E and A squared. Right? That's what H is from here. Okay, so let's put E here. Now G inverse EG is just E, and E does belong to H. Right? There it is. It's a member. So so this belongs to H. Right? In the case for that member. Now that was pretty trivial. Now. For A cubed, it's not so easy. You can see quite a bit of analysis. All right. Now look, we're talking about D6. So what is the general form of an element, little g, belonging to D6? Well, it'll be of this form, right? It'll be b to power I, now I can be 0 or 1, times a to power j, and because we're talking D6 now, this j can range over 0, 1, 2, 3, 4, 5. Right? Now for